Welcome back to CSAI Think Tinker Learn. This is part of our System Design Essential series. The goal here is to give you a solid mental model of system design topics. We're breaking down graph databases and query models today. This is a concept first introduction to help you build your system design foundations quickly. If you want to see a deep dive on the trade offs or a specific case study, let me know in the comments. Let's get started. To understand why we need graphs, we have to look at the relational bottleneck, what I call as the O log n death spiral. In a SQL database, relationships are handled via foreign keys and joins. If you want to find a friend or friends of friends, you need three joins. Each hop requires scanning a global binary tree index, and each of these scans costs O log n. By the time you reach 4 degrees of separation, your relational database isn't querying anymore. It's just waiting. The performance collapses exponentially as the depth of the relationship increases. The secret weapon of a true graph database is index-free adjacency. This is what separates a real graph engine from a relational database pretending to be one. Finding your starting node still requires a standard index lookup. But once you are there, every move to a neighbor is a direct O1 physical pointer data reference. Neighbors are physically stored together. This means traversal time is constant relative to the number of edges, regardless of how many billions of nodes are in the total graph. The primary engine for most applications is the LPG or labeled property graph model used by Neo4j or and also the Amazon Neptune. In this model, nodes and relationships are peers. Both can hold rich, embedded, key value metadata. It is schema optional and incredibly flexible for evolving domains. This is your go-to for 90% of production apps, social networks, recommendation engines, and fraud detection. It's built purely for speed and deep traversal. The alternative is the RDF data model, the semantic engine. Instead of property bags, it uses triples, subject, predicate, and object. RDF was built for the semantic web and uses strict ontologies to infer relationship across disconnected organizations. While powerful for data interoperability, do not use RDF for high throughput social feed. The strictness and logical overhead will kill your system's velocity. Use it for knowledge graphs, not high speed behavioral data. How do we talk to these engines? Cipher and GQL are the declarative routers. They use an ASCII art syntax where you tell the engine what shape you want and the engine figures out how to find it. Notice the 1.6 index in the diagram. This allows for variable length hops that would be nightmare in a SQL. GQL is the new official ISO standard, finally giving graphs an industry standard query language equivalent to SQL. On the other side, we have Gremlin, the imperative pipeline, part of Apache Tinkerpop. This is a procedural traversal. You dictate the exact physical steps the engine must take. It's a cursor navigating the graph. While it's more verbose than Cipher, it grants ultimate control for advanced optimization. One major warning: if you don't use .dedupe on intersecting paths, your cursor can get caught in infinite loops, walking in circles forever. Under the hood, you need to understand the execution algorithms, breadth first search versus depth first search. Cypher's shortest path naturally uses BFS to expand level by level, making it great for finding the closest connection, but very memory heavy. Gremlin defaults to DFS, which is memory but path blind. It might go down a million node rabbit hole before finding a neighbor two steps away. Know your engine defaults. Let's look at the real topology pattern. Fraud detection using a star topology. We look for shared identity rings, where multiple users converge on a single hidden identifier like a phone number or a specific device ID. In SQL, this requires complex group by and having clauses. In a graph, it's just a structural shape. A senior tip: always scrub default data like a generic 99999 zip code. Failing to do so creates ghost nodes, useless supernodes that crash your traversals. Another common pattern is collaborative filtering for recommendation engines using bipartite traversal. This is the classic customer who bought X also bought Y logic. It is a simple two hop traversal, user to product, to similar user, to a new product. This pattern relies heavily on the edge computing and aggregation to rank the highest signal recommendations. Graphs allow you to do this in real time as the user is browsing, rather than relying on stale batch jobs. In an enterprise environment, we use a hybrid architecture. Don't replace your RDMS, supplement it. Let SQL handle your asset financial transaction and tabular matrix. Let the let the graph engine handle the multi-hop behavioral signal. The critical path here is the synchronization pipeline. Data driven between your SQL ledger and your graph signal is your biggest enemy in production. You need a robust event driven strategy to keep them in sync. When should you reach for the graph? Use them for deep traversals, like 3 plus levels, dynamic schemas, and real time shortest path requirements. Avoid them for bulk aggregation like sum or average over millions of rows. SQL or columnar stores are better there. Also, don't use a graph for shallow one hop queries. Standard B3 indexes are perfectly fine and are much cheaper for simple lookups. Use the right tool for the job. To wrap up, here are your interview flashcards. Remember, index-free adjacency means O1 hop per hop. LPG is for pragmatic speed, while RDF is for semantic interoperability. The GQL is a new ISO standard you should mention to show you are current. Now for the community. Have you ever seen a relational database buckle under the weight of recursive joins? And did moving a graph solve it? Share the sequel to graph stories in the comments. If this helped you, please like, share, and subscribe to CSAI Think Tinker Learn and press that notification icon so that you can get the notification as soon as we post a new video on any of these topics. Check out the site for more essentials. Until next time.